This call is now being recorded.
Okay, so we are now on chapter 5. The chapter 5, we have here the title for chapter 5, Properties of a Random Sample. But before discussing, let me have this introduction for chapter 5. Note that there are two ways of obtaining a multivariate data or multivariate observations. Say, for example, we want to obtain an n observations. So there are two ways of obtaining this multivariate data or multivariate observations. Say we consider an experiment designed to gain information about some characteristic of a population of people. So for the first way, uh, excuse me. Okay, say we let x sub I here for our, say for example, for a characteristic, one characteristic of a person or an individual. Say we have here the weight of a person I. Okay, since we want to obtain an n observation, I is from 1 up to n. So in other words, this random variable x sub I, we have a random variable x sub I, and since I is from 1 up to n, then we have n different random variables. Okay, one random variable for each person. So the random vector that we have here, we have this random vector, a vector of random variables, x sub 1, x sub 2, and so on and so forth. And then we have up to x sub n. Having this random vector of random variables, then we can obtain a multivariate observation, having n observations. So the realized value of this random vector, pwede natin yan siya. This will imply that we have this observation x sub 1, small x sub 2, up to x sub n. Okay? So in other words, we obtain this multivariate data, these multivariate observations, and we can actually obtain this multivariate observation either by or either in a sequential manner or in a simultaneous manner. When we say sequential manner, say we consider first the first person x sub 1, and then we're going to determine the weight of that person 1. So we're able to get its value, that is x sub 1 here. And then next, sequentially, next we get another person from the population, and then we're going to determine its weight. So we have this value, x sub 2, and so on and so forth until we're able to get the nth person in our population, and then we're going to obtain its weight, which is equal to x sub n. So in other words, we obtain our n observations in a sequential manner. But we can also obtain our n observations in a simultaneous manner. That means from our population, we are going to get n number of n number of people, and then we're going to label the first person as x sub 1, and then the nth person as x sub n here, and then we're going to determine the the weights of each person. So we obtain now our multivariate data or a multivariate observations. So in this case, no, in this way of obtaining a multivariate data, the random variables, no, the random variables x sub I are independent, and at the same time they have the same distribution because it refers only to the weight for a certain characteristic, which is the weight of a person. Another way of obtaining a multivariate data or n observation, the second one here, in which we consider the x sub I here, okay, the x sub I here, pwede na siya some characteristics of a person, okay, of a person. Say for example, we let x sub 1 here, ang iyahang weight sa person. Ang x sub 2, pwede na siya, mao ni ang iyang height. And so on and so forth. Up to, say, we have here x sub n. Pwede natin sabihin ang kanyang age. Okay? So for a certain person, for a particular person, we were able to obtain a multivariate data, an n observations. So, in other words, we obtained this random, okay? We have this characteristics. So we have this random vector of random variables, x sub 1, x sub 2, and so on and so forth, up to x sub n. And then this would imply that we can obtain now the n observations, x sub 1, that's for the weight of that person, x sub 2, that's for the height of that person, and so on and so forth. And then the small x sub n, we have this value for the age of that person. So in this case, now in this way of obtaining the n observations, the random variables x sub I are not independent. Okay? Naintindihan nyo ba? Hello guys. Well, in the first way of obtaining the n observations, we have independent and independent. At the same time, they have the same distribution. We have independent random variables and have the same distribution. Okay, so I hope that you understood these two ways of obtaining a multivariate data or a multivariate observation. In this case, we want to obtain n number of observations. So let me proceed now to the properties of a random sample. Okay, before you're going to know or determine the properties of a random sample, you must understand first the mathematical definition of a random sample. So we have here in definition 5.1.1. The random variables x sub 1 up to x sub n are called random sample of size n from the population with distribution function or the density function or probability density function f of x. If, says here, if x sub 1, so on and so forth, x sub n are mutually independent random variables and the marginal PDF or PMF of each x sub I is the same function f of x. So if we look at the definition here, it's actually obtaining a multivariate data using the first way, yung first way of obtaining a multivariate data, in which the random variables x sub 1 up to x sub n, they are mutually independent random variables, and then the marginal PDF or PMF of each x sub I has the same function f of x. So alternatively, these random variables x sub 1 and so on and so forth up to x sub n are called independent and identically distributed random variables with PDF or PMF f of x. So this is commonly abbreviated as IID, or random variables. By the way, there are things that you need to know for this definition 5.1.1. Based on our definition, the sampling method of the data collection here is usually sampling from an infinite population. Okay, we consider here an infinite population. So in other words, we obtained the values of our random variables x sub 1 up to x sub n in a sequential manner. Say the value of the random variable x sub 1, we have small x sub 1, that's the realized value. The value for the random variable x sub 2, we have the small x sub 2, that's its corresponding realized value, and so on and so forth. If we're going to obtain these observations from an infinite population, if we're going to remove the realized value x sub 1 there, the realized value of x sub 1 in our infinite population, still the random variables x sub 1, x sub 2, or the x sub 2, x sub 3, and the other random variables are independent. That is why the definition for random sample in 5.1.1 is satisfied. But if we consider that our population is finite, if the population is finite, the sampling that we're going to apply here is sampling with replacement. Okay, sampling with replacement, because it would lead us to a random variables that is independent. Using this sampling method. Okay, so we have there x sub 1 up to x sub n, they are mutually independent random variables, and then the marginal PDF or PMF for each x sub I is the same function f of x. Okay, based on definition 4.6.5, in which we have the joint PDF or PMF of x sub 1 and x up to x sub n, we have here the assumption that the random variables x sub 1 up to x sub n are mutually independent. So the PDF, okay, pwede naman ganito. We have here, that's the PDF. By the way, we can, kalimutan ko tuloy, we can denote our random vector here as a bold X, having this vector of random variables, x sub 1, x sub 2, and so on and so forth, up to x sub n. Okay, so this is now, this random vector is a random sample. If it is a random sample, it is a random sample if, oh no, it's a random sample if the random variables x sub 1, x sub 2, and so on and so forth, up to x sub n, are IID. Okay, so based on definition 4.6.5, in which we assume that the random variables are mutually independent, then the PDF of this random variables, or pwede naman ganito, no? We have that notation. Okay, so we have here the product of the marginal PDF or PMF. Okay, so we have here, since we assume that they are mutually independent, or this is equal to the product, using the product notation, f of xi, I from 1 up to n. But if we're going to add an additional assumption that the marginal PDF or PMF is the same, in other words, identically distributed, we can further uh, write this as f of x, okay? The same, pagpareho lang yung kanilang, identically distributed with the PDF function or the probability mass function f of x, and that would be raised to n. By the way, pag ang assumption na dito, we have now an IID, okay? Random vector or random variables. So we have that. Pero pag independent lang, mutually independent, then we have this. The product of f of x sub I from 1 up to n. Okay? So the joint PDF or PMF can be used now to calculate probabilities involving the sample. Okay? If we have a PDF or a PMF from a member of a parametric family, say we have a parameter now that we're going to consider in our probability density function or the probability mass function, we can denote our PDF or PMF by this. This is now condition, no? That is condition on our parameter theta. In other words, with reference to the parameter theta. So we have here the product of this, the product of the marginal PDF or PMF, I from 1 up to n. Okay, so let us now have an example. Say we have a random sample, x sub 1 up to x sub n from the exponential beta population here. Obviously, if we have this random variable x from the exponential beta distribution, okay, that implies that the PDF for this would be equal to 1 over beta e to the negative x over beta. Okay, that our x here will be greater than or equal to 0. So we have a random sample from an exponential beta population. Now if we're going to determine the joint PDF of the sample, so we have here, and since we have a random sample, that means IID, atong mga random variables. So pwede natin gamitin lang yung definition natin for the independence, so the product of the marginal distribution, and then we just substitute the distribution, the PDF, for each x sub I, and then after that, apply, okay, the product operator. Then we obtain this for our probability density function of our random sample. Then we can now use this PDF of our random sample to compute, say, the probability that x sub 1 greater than x sub 2 and so on and so forth, x sub n greater than 2. So according to our definition, that would be equal to this multiple integrals, indefinite integrals. Then we have here this is our PDF. Okay, that's the PDF of our random sample. So evaluated to dx sub 1 and so on and so forth up to dx sub n. And then integrate out x sub 1. So in other words, you're going to apply the integral. This a multiple integral, 1 by 1, first for x sub 1, integrating out x sub 1, then after that, integrating x sub 2, and so on and so forth. Then we're able to, we have this. Pwede naman natin yan siya ma-verify. Say, for example, for a generic, natay generic na integral. The exponential So we have the exponential 1 over beta, the exponential of negative x over beta. Say we have here dx. Okay, say we let u here to be equal to negative x over beta. So the differential of u is equal to the negative 1 over beta, the differential of x. So this is just equal to the integral of e to the u, and then we have here negative du. So we have negative e to the u, and this would be just equal to negative e to the negative x over beta. Okay, so uh, yung sakan, if you're going to integrate out x1 here, x sub 1 here, then we have here uh, or say for example, we have here uh, negative 2 to the positive infinity and so on and so forth. Then we have here 2 to the positive infinity. Then we have here the integral 2 to the positive infinity. And then we have here 1 over beta and e to the negative x sub 1 beta. Then we have here dx sub 1. And then we have here dx sub 2 dot dot dot. We have here dx sub a dx sub n. So if we have the integral 2 to the infinity of 1 over beta e to the negative x over beta, this is actually equal to the limits of here 2 to the b 1 over beta e to the negative x over beta b approaches to positive infinity. So this is equal to the limits. We have that as our answer. Negative e to the negative x over beta evaluated the 2 to b, and then b approaches to positive infinity. Okay, so we're able to get here e to the negative apply. We have the limit for this, the limit. Then we have negative of e to the negative beta, b over beta, then minus minus, so we have plus e to the negative 2 over beta. Then b approaches to positive infinity. And we have here, the value for that is e to the negative 2 over beta. So we have here. So itong part na to, if we're going to evaluate this, itong part na to, we're able to obtain this value. Okay? Uh, applying the same procedure, hence we're able to obtain this value. By the way, wala na ito gigamit diyan ni ang ato ang identically distributed na assumption. So next, if we want, we have a random sample. Now we're going to apply the identically distributed assumption here. If we're going to compute for this the same probability, the probability that x sub 1 greater than x sub 2, x sub n greater than x sub n, okay, that's by independence. We have the probability of x sub 1 greater than x sub 2, and so on and so forth, the probability of x sub n greater than 2. And then since they are identically distributed, okay, we can just have the probability of x sub 1 greater than 2 raised to n. And then applying this, ito, evaluating this, we have already here, itong part na to. Ito, dito na parts. Okay, so itong part na pala dito, no? You have this part, e to the negative 2 beta, that is raised to the n. Okay, so we obtain the same answer. So we're able to determine the probability using the PDF of our sample uh, in two ways. Yung kanina, itong first part, we just use the mutual independence property. And then itong sa pangalawang part, we apply the assumption of independence as well as identically distributed random variables. Okay? Any questions or clarifications for the first section of chapter 5? Yun lang naman, no? We have the PDF of our random sample. Okay, let's proceed now to the next section, sums of random variables from a random sample. So we have a random sample, x sub 1 up to x sub n is drawn, and then some summary of the values is usually computed from this sample. So any well-defined summary may be expressed mathematically as a function t of this realized value of our random sample, whose domain includes the sample space of the random vector x sub 1 up to x sub n. Take note na itong random vector natin dito, this actually refers, no, pwede naman natin yan for this bold x here. So in other words, this bold x here is a function from the sample space S to the set of n-dimensional set of real numbers. And then we have here our function t here. Okay, our function t. In other words, if we have an element in our sample space, so the image of that element under, x here, that is x, random vector x of omega. Then we have here the n tuples of real numbers, element of r to the n. So we have x sub 1 and so on and so forth up to x sub n. So ito ngayon yung ating n observations. That is why we have this t here based on this sample point. Meron tayong sample point na ngayon. Then we have here the image could either be a real number, pwede siya real number. It could also be a vector of real numbers, say r to the n under t. So in this case, we have here tx1 and so on and so forth up to x sub n. It could either be an element of, pwede siya r lang siya, a real number, or it's an element of r to the n. Pwede naman yan. Okay, so that is our function t. So the function t may be real valued, it says here, it's a real valued, itong part na to, it's a real valued, or a vector valued. So in this case, vector valued. So thus, the summary, the summary is a random variable. It could be a random variable, y. Pwede natin ma-express yung t as a random variable y. Okay, it says here that since the random sample has a simple probabilistic structure, being an IID, then the distribution of y is particularly tractable. And we call the distribution of y taken from the variables in our random sample as the sampling distribution of y. So because of that, we have a random sample, the random variables of our random sample. So for this particular section, we are going to discuss some properties of the sampling distributions. In other words, some properties of our random variable. And usually the random variable here having the sampling distribution, we call it as a statistic. Okay, statistic. And the form for that would be sum of random variables, defined by the sums of random variables. Okay, so definition 5.2.1, let x sub 1 up to x sub n be a random sample of size n from the population And we let t of this realized value be real valued or vector valued function whose domain includes the sample space of this random vector, then the random variable or the random vector y, okay, which is a function of t of our sample point, will be called a statistic. And the distribution of that is called the sampling distribution of y. Okay, so the definition of a statistic is a very broad, with the only restriction being that the statistic cannot be a function of a parameter. Okay, now we're going to consider three statistics that are often been used as a good summaries to our sample. The first one, we have the sample mean. Okay, we have the arithmetic average of the values in a random sample. It is usually denoted by x bar. So itong x bar natin, because it's a statistic, it's actually a function of our sample point. So pwede natin ma-express ito na t, no, pwede naman yan, t of x sub 1, x sub n. It's a function of this random sample. Okay, so ito ngayon yun. Pero ang pagka-express na lang natin ng x bar ngayon is in terms of this formula. So the summation of the finite, or rather 1 over n, the finite summation of x sub I. The sample variance is the statistic defined by s squared 1 over n minus 1 times the finite summation of the square of the deviation of x sub I minus x bar. Okay, I from 1 up to n. Okay, pwede din naman natin ma-express dito, according to our definition, this is a sum, no? A function of our random sample. So t of x1, so on and so forth, x sub. Okay, then the sample standard deviation defined by the square root of s squared, and that is s. Kaya ang sinabi dito, no, we actually suppress the functional notation here in the above definition. Say s, pwede siya ganito. Pwede pala itong x bar, itong s, sa itong s dito, it could be either s, x1, dot, 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 up to s. Okay, so we just omit now this expression of our random variables. Okay, having this summaries, no, statistic, we consider the realized value of the sample mean as this small x bar, the realized value of our sample variance, this s square, and then for the sample standard deviation, we have small s. Okay, so we are going to derive now some properties of our sample mean and the variance. But first, we're going to consider this theorem. Let x sub 1 up to x sub n be any numbers, and then x bar be equal to the sum of x sub 1 up to x sub n over n. And it says here that the minimum of this finite summation of the square deviation of x sub I from a, I from 1 up to n, the minimum for that, when we choose a here, no, to be equal to x bar. So we have now the finite summation of the square deviation of x sub I minus x bar I from 1 up to n. And then for letter B, we have the product n minus 1 times s. That's equal to this summation, according to our definition for the sample variance. And that would be equal to this expression. The finite summation of x sub I square, then I from 1 up to n x bar square. So to prove letter A, so we add and subtract x bar. That's the first equality. And after that, we're going to expand using the expand this expression. And after that, apply the property of summation. Then we have this. Okay, we have that. sum of three terms. And then since we know that the first central moment is equal to 0, for this, it does not depend on the index of our summation. We can write it before the summation symbol, but the summation of x sub I minus x bar is actually equal to 0. Hence, the second term will be just equal to 0. So what remains the first term and the third term. So it's now clear that the right-hand side of our equation is minimized when we choose our a here to be equal to x bar. Because if a is equal to x bar, this term will become equal to 0. Okay, it's been minimized when we choose our a here to be equal to x bar. So to prove letter B, we just take our a here to be equal to 0. So if a is equal to 0, so from here, in the right-hand side here, we have here the, if a is equal to 0, then we have this finite summation of x sub I squared, I from 1 up to n. And then in this case here also, for this, when a is equal to 0, we have here the finite summation of x bar quantity square, I from 1 up to n. Okay, since this does not depend on the index of our summation, we have n x bar square. Okay, so we have that here. And then the summation, finite summation of x sub I. Okay, so we're able to obtain this finite summation. Okay, so uh, now we're going to study the sampling distribution by considering the expected values of the sum statistics. So we're going to use this lemma. We have a random sample x sub 1 up to x sub n from the population, and we let g sub x be the function such that the mean of g of x1 and the variance of g of x1 exist. Then it says here that the expectation of the finite summation of g of xi, I from 1 up to n, will just be equal to n times the expectation of g of x1. Okay, this is easy to prove using the linearity of expectation. So the expectation of the sum will just be equal to the sum of the expectation. And since we know that the x sub i's are random sample, they are independent, random variables are independent, then functions of independent random variables is also independent. Hence, we're able to obtain this expression on the right-hand side. Okay, the proof for 5.2.2 is quite lengthy. You can check in the book for the proof of this second result, that the variance of the finite summation of g of x sub I from 1 up to n, will just be equal to n times the variance of g of x sub 1. Okay, so this time we're going to proceed to theorem 5.2.6. We have a random sample from a population with mean mu and then a variance sigma square that is finite. Okay, take note that the distribution here is not defined in theorem 5.2.6. Hindi naka-define yung ating distribution. But if we have a random sample, it says here that the mean or the expectation of the sample mean will just be equal to mu, or the mean of the sample mean will be equal to mu. And then the variance of the sample mean is equal to sigma square over n. And then the expectation of the sample variance will just be equal to sigma square. As I have said, the distribution of this random sample in this theorem is not defined. So, pwede siya kahit anong distribution. Pwede siya normal. Kung random sample from a normal distribution, still, yan yung i-discuss after, that the mean of the sample mean will just be equal to mu. But if the random sample is of different distribution, still we get the sample mean, or the expectation of the sample mean will just be equal to mu. So we have here the proof. The expectation of x bar So the first equality, we just substitute the definition of x bar, and after that, uh, the property of our expectation operator. Okay, since we know that the mean of our random variables x sub 1 or x sub I are the same, up to x sub n will just be equal to mu. So this one will cancel out. Then we get n, and this one is equal to mu. And then for the variance of x, the first equality, we just apply the um, definition for the sample mean, and then apply the property of the variance. Okay, the variance of 1 over n, the summation of x sub I, that would be equal to 1 over n squared. That's a property of the variance times the variance of the finite summation of x sub I. And then we have that uh, using this lemma, itong lemma in equation 5.2.2. So that's n times the variance of the function of g sub n. So 1 over n squared. So ito ngayon, n times the variance of x sub 1. Okay, since we know that the variance of x sub 1 here is a sigma square, okay, cancel yan. Ang maiiwan na lang ngayon is sigma square over n. Okay, so we're done with letter B. So let's proceed to letter C, that the expectation of s squared will be equal to sigma square. So first equality here, we just apply the definition, okay, for s squared. Itong part na to yung sa theorem 5.2.4. Ito. Okay. Itong part na to. So, sabihin natin, capital na lang yan siya. That would be equal to yung n minus 1 man yan. Equal siya this. X sub I squared. Because we're dealing with expectation, so we're going to use the random variables. Okay? So, S squared now. The statistic S squared is 1 over n minus 1 times, okay, random variables tayo. Okay, yan yung ating apply dito ang part. So here. Then applying the linearity of the expectation operator. So we have that. So applying. Okay, so itong first term dito, we apply our lemma 5.2.5, the equation 5.2.1. Okay, we have the expectation of the finite sum of a function, no? Expectation of a finite sum of a function of x sub I. Okay, so ito yung result, n times the expectation of x sub 1 squared. And then, since we know that the variance, yung variance ng x sub 1 natin, that would be equal to, okay, the expectation of x sub 1 square minus square of that. So here, we're looking for this. So there's the variance of x sub 1 plus the square of the mean. So n, ito yung n. So the variance of x sub 1, given yan siya, sigma square, plus the square of the mean, x sub 1. Okay. The same thing, ganito. Ito rin. We're going to apply it here, the same form. So that actually the variance, no, the variance of the sample mean, we already obtained that. We have here. So ito yung variance of the sample mean. Plus, okay, plus the square, no, the square of the mean of the variance. Rather, the mean of the, or the expectation of the sample mean. Yan. Simplifying here, we're able to get sigma square. Okay, so we're done with 5.2.6. Okay, so The next section here, the next paragraph here uh, implies that we're going to discuss in detail the sampling distribution of the sample mean. We already know that the mean of the sample mean is equal to mu. The variance of the sample mean is equal to sigma square over n. But we do not know yet what is the distribution of the sample mean. Okay, so uh, let's consider first this simple relationship na meron akong formula, na meron akong solution dyan. Say, we let y here to be the summation of x sub I from 1 up to n. So the finite summation of x sub I. Okay, since x bar here from our notation, from our definition is equal to this. So if we have f of y is the PDF of y here, then it says here the PDF or the distribution function or the density function of x bar here would be equal to n times f of x sub n, which is the PDF of x bar. Okay, so another problem in the problem set, try to prove that this is true. This statement is true. So we have this relationship now between the sample mean, and then the finite summation of the random variables x sub 1 up to x sub n. Yan yung kanyang relationship itong dalawa na to. So the density of the sample mean is equal to n times the density of y evaluated at n times x. Okay, madali lang masyado ito. You can apply what you have learned in the previous chapter. Okay, so another relationship that will hold for the moment generating function. This is still between y, which is the finite sum of the sample, the finite sum of the random variables and the sample mean. So the moment generating function of the sample mean will just be equal to the moment generating function of the sample mean evaluated at t will just be equal to the moment generating function of y evaluated at t over n. Okay, madali lang masyado yung ito yung explanation dyan. This is by definition. First equality by definition. Second equality, you just substitute what is x sub n, or rather x bar here, and then after that the property, okay, the property of independence, as well as the property of independence, as well as identically distributed. So we have that. Okay, since x sub 1, it says here x sub 1 are identically distributed. So if they are identically distributed, the moment generating function of x sub I evaluated at t is the same function for each I. Okay, let's proceed now to theorem 5.2.7. We have a random sample x sub 1 up to x sub n from the population with moment generating function, given yung moment generating function. Then the moment generating function of the sample mean, yung sample mean na ngayon, this is the moment, would be equal to the nth power. Okay, the moment generating function of the sample mean evaluated at t is equal to the nth power of the moment generating function of x evaluated at t over n. Okay, we have here the proof. So first, this by definition here. Okay, this is by definition. Second equality, substitution for the value of x bar. And then after that, the property of the exponential function. And then after that, applying the independence property, assumption of our random variables. So If random variables are mutually independent, then functions of these random variables are also uh, mutually independent. Kaya we have the product of the expectations. And since then here we apply, they are identically distributed. So we have the nth power of this expectation. And then again, applying the definition of the moment generating function. So we're able to obtain that uh, expression. Hence, the theorem is proof. Okay, so we're going to apply it now to a particular example. Say we have the distribution of the mean in which we have a random sample coming from a normal population, normal family, no, with parameter mean mu and variance sigma square. So the MGF of the sample mean from here, uh, itong equality na to, that's using our result above, theorem 5.2.7. So the moment generating function of the sample mean evaluated at t will just be equal to the nth power of the moment generating function of x evaluated at t over n. And then noting that if we have a random variable having a normal distribution with mean mu and variance sigma square, ito yung form ng kanyang moment generating function. So we just replace t here, itong t dito, we just replace t here by t over n. Kasi ito man yung i-evaluate natin. So we have now e to the mu t over n, and then sigma square, instead na t square lang doon, ito t square lang. So we have t over n quantity square. And then in this case, if we have exponential of a function, okay, pwede natin sabihin na e to the x over n. Equal ba siya? But equal siya sa e to the n x. Ito, exponential of, say this is our x quantity. Okay? Quantity. Equal daw siya sa e to the nx. Okay. E to the n x. Parang ganun. Ano natin nakuha yan? Say for example, we let this y here to be equal to that. If we're going to apply the log, supposedly ln to, because it's the natural logarithm of y. Pero kung mat tayo, kailangan talaga ln. Kasi dito sa stat, yung log dito, sometimes it would refer to the natural logarithm. So we have here the ln. Okay. Apply for that. So we have here n times the ln of e to the x, and that is equal to nx. Okay, so we have here ln of y. So if we're going to apply, this would imply now e to the ln of y, e to the nx. So we have y is equal to e to the nx. Okay, ito, totoo ito. Ayan, part na yan. So that's why now we have exponential of nx. And then, calculus lang naman to, or algebra. Simplifying, then we have this. Okay, so since we obtained this expression now, observe that this is the moment generating function, no, moment generating function of the random variable having random variable having a normal distribution with mean mu, and this time the variance uh, is sigma squared over n. Therefore, using this technique, this MGF technique, we were able to determine the distribution of the sample mean. So yung distribution ng sample mean natin dito na case, okay, when we consider a random sample from a normal distribution, that the mean of the sample mean, or rather the distribution of the sample mean, also has a normal distribution with mean mu and variance sigma square over n. Okay? Say another example. Kunwari, gamma naman yung ang ating napili. So, if we have a random variable here, meron tayong random variable x here, having a gamma, alpha, beta random variable, ito yung kanyang moment generating function. Evaluated at t. So we have here the alpha power, or 1 over 1 minus beta t raised to alpha. Okay, so for this particular family of distribution, let us now try to find the distribution of our sample mean. Okay, so we have here the moment using the MGF technique. So the moment generating function of the sample mean evaluated at t. Okay, using our result in the previous theorem, that is equal to the nth power of the moment generating function of x evaluated at t over n. Okay, so ito na ngayon. We just replace t here, itong t na to, by t over n. Ayan. So ito na yung result natin. Replace the t over n. So ito na yun, t over n. So the alpha power of this, and then raised to the n. And then simplifying, and then we have this expression. And then observe, you can observe, halos pareho naman yung form nila. Kung titingnan ninyo, itong form na to, at saka yung form na to, pareho lang. Okay? So that means the parameter here, yung parameter natin, we have still have a gamma distribution for our sample mean with parameters n alpha and then beta over n. So yung alpha dito dapat, ito na ngayon, n alpha. Itong beta dito, ito na ngayon, beta over n. So that's the distribution of the sample mean when we consider a random sample from a family, from a gamma, alpha, beta family. We apply the moment generating function technique. Okay. May sa next natin na paragraph, it says there, supposing yung theorem 5.2.7 is not applicable. In other words, either the resulting MGF of x bar is unrecognizable. We cannot recognize the resulting MGF, or yung population MGF does not exist. So we're going to apply the transformation that we have learned in sections of 4.3 and 4.6. Yun naman ang transformation method that we have. So we're going to find the PDF of this statistic, which is the finite summation of the random variables. To find the PDF, at the same time, the PDF of our sample mean x bar. So in such case, we have what we call the convolution formula. So theorem 5.2.9 says here that if x and y are independent, continuous random variables with PDFs, f sub big X of x, f sub big Y of y, then the PDF of z here, which is the sum, okay? The sum of two independent continuous random variables. So this is now the PDF. We have this improper integral of f of x evaluated at w, f of y evaluated at z minus w dw, negative infinity to positive infinity. Again, as I've said, we apply here what we have learned in section 3 up to section 6 of chapter 4. Notice na dito sa theorem na to, we have these original variables in terms of x and y. And what is our transformation? So we let w be equal to x. We let z be equal to x plus y. Okay? Hindi naman nakasulat dito ngayon. Ano yung script A natin dito? Ano yung script B natin dito? Actually, yung script A natin dito is the set of all ordered pair. Kung i-detail natin yung pag-derive natin dito, supposedly meron tayong script A here is a set of all ordered pair x, y, such that the joint, yung joint density to be positive. And then we have here script B here is the set of all, this case W and then Z, such that yung W natin dito equal siya sa X, yung Z natin dito, okay, what do you have? For Z, okay. X plus Y, tama pala. X plus Y. Such that for some, yan sabi natin, for some XY in script A. Okay. I-check muna natin kung nag-exist ba, meron bang one-to-one transformation from script A to script B. Kung merong one-to-one diretso, di na natin kailangan i-partition yung script A natin dito. So, we have this transformation. X equals to W, Y is equal to Z, minus W, it says here, if and only if naman to. If and only if. Yan yung transformation natin. So, this implies that we have a one-to-one transformation from script A onto script B. Okay, so in other words, for each WZ in script B, there is only one XY in script A that satisfies our transformation. Okay, so kung ganun yung mangyari, hindi na natin kailangan i-partition yung ating script A. We get the partial derivatives of this, the partial derivative of x with respect to W, partial derivative of x with respect to Z, partial derivatives, derivative of y with respect to W, then we have that. And then we have here the Jacobian of our transformation. So kung yun itong Jacobian ng transformation natin ngayon, then we can now obtain the joint. Ito ang tawag natin, the joint PDF. The joint PDF of Y and Z. That will be based with the joint PDF of X and Y. Okay. So ito ngayon. You have that. Ito yun. Times the absolute value of the Jacobian of our transformation. Since we know that we have independent continuous random variable, then the joint PDF will just be equal to the product of the PDF. And then the absolute value of J will be just equal to 1. So kung mauna nga ito ang joint PDF of W and Z, we can now determine the marginal PDF of Z. So this is now the marginal PDF of Z. That's actually, by definition, the improper integral of the joint Ito yung joint. So Z man siya tayo, so it must be we integrate it with respect to W. So, so we have that, and then from negative infinity to positive infinity. That's actually the proof for that theorem. Yan yung sinabi niya dito. Madali lang siya. So, konti lang masyado yung proof. So we have that in detail na sa itaas. Okay? So if we have independent, continuous random variables, and then if we're going to determine the distribution of the sum of these two independent, continuous random variables, then we're going to use theorem 5.2.9. Okay, let's have an example to illustrate this theorem. Okay, supposing we have the sum of the Cauchy random variables. So, kani siya nga example, no? This is an example in which the moment generating function or the MGF technique will not be applied. Say for example, we want now to determine meron tayong sum of Cauchy random variables. Now we're going to determine the sampling distribution of the sample mean, in which we have a random sample from family of Cauchy distribution. Ito ngayon yung example na yung MGF technique will not apply. Okay? So, say for example, now we apply the previous theorem now. Say we let U and V be independent Cauchy. So, U to be a Cauchy, 0, sigma. And then V having a Cauchy distribution, 0, tau. That is, ito yung nasa kan, ito yung kanyang probability distribution function. That's for U, and then this is for random variable Z. Okay, so the original variables here is U and V, and then since we're going to use the previous theorem, that is in terms of W and Z. So we use the random variable for our transformation, W be equal to U, and Z be equal to U plus V. Those sa theorem natin, X plus Y, X and Y man yung random variable, original. And dito sa example na to, yung ganamit na original na variables, U and V. Again, you can choose. No? Clearly see in our transformation that we have a one-to-one transformation from script A onto script B. Hence, we can now apply the theorem. So the marginal, ito na yan, the marginal distribution of Z. Z is the sum of these two random variables, U and V. So we have here the integral. Yung sabi doon, no? Itong part na ito. So the integral of the product of the density of U evaluated at W times the density of the variable V evaluated at Z minus W. So papalitan naman lang dito, itong sa U, you replace this by W. Itong V dito, replace it by Z minus W. Kaya ito ngayon. Okay. How are we going to evaluate this improper integral? Siguro, you can still recall this improper integral, no, using partial fractions. You have learned that in Math 61, no, partial fraction decomposition. Exercise yan siya. Pero hindi ko na lang ibigay sa inyo as a problem set. So, if you have some time to evaluate this improper integral using partial fraction decomposition, we can obtain the marginal distribution of Z. Ito ngayon, the PDF of Z to be equal to this. Okay? So, yan yung ating PDF for Z. Okay lang ba, no? Naintindihan nyo ba na hindi ko na kailangan na We don't need to show the solution to this integral, improper integral, using the partial fraction decomposition. We have that result. So if we have that PDF for z, in which z is the sum of two Cauchy random variables, anong ibig sabihin yan? The sum, kung titingnan mo to, okay? Kung titingnan mo yung form ng ating PDF of z, halos pareho lang din sa PDF ng Cauchy. O kung titingnan mo itong form na to, yan. At saka ito, halos pareho lang ang kanyang form. So, ibig sabihin yan na ang sum of two independent Cauchy random variables is again Cauchy. No? It's again Cauchy with parameter 0, ito 0, and then sigma plus tau. So the scales parameter, we add the scale parameter. Pero yung ating location parameter is actually a constant 0. Cauchy. Pero ano yung goal din natin dito? We're not only looking for the distribution of the sum of these two random variables u and v, but we want also to determine the distribution of the sample mean, the z bar. So to determine that the sample, no, the sample, the distribution of the sample mean, if we have a random sample, no, if you have a random sample z sub 1 up to z sub n from a Cauchy 0, 1, from a Cauchy 0, 1, okay, according to what I have discussed a while ago, itong i-consider natin dito, dalawa lang, u plus v, Cauchy yung u, Cauchy yung v. Eh ngayon, kung meron tayong n number, n, no, z sub 1, z up to z sub n. So, using the principle of mathematical induction, kasi 1 lang yung kanya, 1 lang yung kanyang scale parameter, constant siya. So, kung hanapin natin yung sum ng z sub 1 plus z sub 2, so isa Cauchy, 0, 1 plus 1, 1 plus 1, yung ganon. Yan yung sa first step, no? Pag mag-discuss ka ng principle of mathematical induction, consider, say, when n is equal to 2, then you're going to show that your statement is true for n is equal to this, and then for n is equal to n plus 1. N is equal to k, and then you're going to show that it is also true for n is equal to k plus 1. Ito yung makikita nyo. So this is a problem set. Again, you apply the principle of mathematical induction. Hindi lang, madali lang masyado to. So easy. You just apply the principle. Andiyan naman, meron na kayong format on how to show sa itong first part lang. When you have two random variables, and then you're going to show that for, okay. And then, lastly, you're going to determine now the distribution of z bar, yung sample mean na z bar. And you can verify kung ang sum, ang finite sum, Cauchy 0n, 0 and n, yung distribution ng sample mean is Cauchy 0, 1. Pareho lang sa ating random variables. So easy. Take this as a problem set also. Any questions or any clarifications? I just want to emphasize here that in this example, the MGF technique cannot be used for this particular example. Though in the previous example that we have, if we have a family of normal distribution with parameters mu and sigma square, we're able to see that the distribution of the sample mean x bar is also normally distributed with mean mu, and then the variance is sigma square over n. In the previous result, in the previous lemma, we don't. That is for any distribution. The mean of the sample mean is still equal to mu, or expectation of the sample mean is mu. The variance of the sample mean is sigma square over n. And then we apply also the MGF technique. When we have a family of a gamma distribution with parameters alpha, beta. Again, we have seen, using the MGF technique, that the distribution of our sample mean has also a gamma distribution. And this time, the parameters now, we have n alpha, and then the other parameter is beta over n. Itong last na example natin dito, in which the moment generating function technique is not applicable, then we have used the convolution formula to be able to determine first the distribution of the finite summation of our random variables, and then itong part na to is so easy. It's so easy because I already said a while ago the relationship of the finite sum. We denote that a while ago by y and then x bar. So kaya ito madali masyado to be able to prove that one. Nakuha niyo ba ako? Guys? Ito kanina. Yung relationship ng y, which is the finite sum of the random variables and the sample mean. Ito yung kanya. Na-prove nyo naman yan. Madali din masyado yung mag-prove. That is the relationship that you're going to use, especially when the MGF technique fails and you want to determine the distribution of the sample mean. Guys, are you there?
Yes, sir.
Okay. Any questions or any clarifications? 7 minutes na lang. Actually, gusto ko sanang tapusin itong section 2 of chapter 5. We still have a location scale family, and then we have also the exponential family. Again, ang desire natin dito, kung meron tayong location scale family, at the same time, an exponential family, ganun din. Determine the distribution of the, kasi yung sa introduction pa lang kanina sa chapter 5, we focus on the sum, the sum of our random variables. Yung sample mean, meron namang sum of this random variables din. Over n lang naman yun. So, ito ngayon, say for example, we are sampling from a location scale family, and then after that, we are sampling from an exponential family. So, kung ang family ng distribution belongs to an exponential family, meron siyang technique on how to be able to be able to determine the distribution of the sum of random variables, at the same time the mean of this the mean of this family of distribution of random variables. Kung ang ating distribution ngayon, it belongs to a location scale family or location family, kasi general naman ito. Pwede siya sa location family, it belongs to a location or scale family, or it belongs to a location scale family. Then we can also determine the distribution of the finite sum of these random variables as well as the distribution of the sample mean. And I'm going to discuss that tomorrow na lang. Ko naman day. Thursday. So that's for end na yun na to ang chapter 2 chapter 2 section 2 for that discussion. And then I'm going to proceed to the next section in which we have sampling from the normal distributions or normal distribution. So para mag-focus tayo sa random sample having a family of normal distribution with parameter mu and sigma square. Ano yung mga properties na ating malalaman dyan? That's for section 3. And then for section 4 of chapter 5, we have the order statistics. The order statistics, we're going to determine the distribution of these order statistics. And then section 5, we'll now discuss the convergence concepts. So for the convergence concepts, we have 3. Convergence in probability. Okay, sometimes we call that is convergence in measure because a probability is a measure. And then the other convergence concept, that is convergence almost surely. Kung sa math pa yan, convergence almost everywhere. And then lastly, we have what we call the convergence in distribution. Not only that we're going to learn these 3 modes of convergences, but the application of these modes of convergences. In the convergence in probability, we have this result application, what we call this the weak law of large numbers. And then for convergence in almost surely, we have the strong law of large numbers. Okay. Then we would also learn the central limit theorem here. That's for section 5 of chapter 5. Sabi ko sa inyo, mas mahaba itong chapter 5, and then somehow we have a quite a harder concepts here that we must going to learn. And then lastly, kung makakaya pa rin sa time natin, we have what we call the methods of generating a random sample. I already discussed this. If you are present, if you have able to review my video recordings about the probability integral transform, I think kung naka-recall kayo dun, the probability integrals transform, you're able to generate a values of a random variable generate a values of a random variable having a particular distribution. Okay, so that's all for this afternoon. Nagsimula tayo sa random sample. Dapat malalaman nyo ano itong random sample. This is why I review the 2 ways of obtaining the a multivariate data. So pag pag yung mga random variables are not mutually independent, hindi na siya random sample. Mutually independent, at the same time identically distributed, then we have a random sample. Then, any questions or clarifications now? PMI, Principle of Mathematical Induction. Sa mga 17 naman yun na. Kasi, Z sub 1, Z sub 2, ito yung nasa itaas. Z sub 1, Z sub 2, ito yun, naka-bracket yan na blue. if you have two random variables, you take first the 2. So hanapin mo yung kanyang distribution ng sum of these two random variables. Eh kung tatlo na siya, so x sub 1, z sub 1 plus z sub 2 plus z sub 3. Ano yung distribution niya? Eh kung yung itong case na to, ang distribution ng sum ng z sub 1, z sub 2 up to z sub n, ay yung Cauchy. Cauchy daw. Cauchy 0n. Eh itong kanina sa example natin, yung scale parameter natin is sigma and tau. Ito, sigma and tau. Eh ngayon, 0, 1 naman tayo dito. Ibig sabihin na this is a standard, having a standard PDF. It does not depend on any parameter. Constant lang siya. So yung sigma dyan, 1. Yung tau dyan, 1. Okay. So kung n number of random variables siya, so 1 plus 1 plus 1 plus 1 up, that would be equal to n here. Ano pa yung isang question? Okay ba yan? Gamiton. Optimizer ang pag-show namin. Yeah, that's for the first. Etong part na to. Problem set. Apply PMI here. Well, for this, you're going to apply the relationship between the finite sum of random variables and the sample mean. Okay. So ready for 32. Any questions or clarifications? Guys, napamudi na, guys?
Nga po, sir.
Ano pa?
Wala, sir.
Sir, kanang sa problem set sa number sa chapter 5 kay PS3 na sir?
Yeah. Yeah, problem PS3 ni siya chapter 5. Problem set. Wala pa ko nakahatag tayo kung sapat ang madugang nato sa problem set 2. For chapter 4. Kani siya sa chapter 5 ni siya. PS3, problem set number 3. What else?
Wala na siguro sir.
Oh, wala na. Okay, sige. Okay, so guys, that's all for this afternoon. I'm going to stop now the recording. Okay. So